The old parable of the country kid moving to the big city and leaving the farm behind is a timeless yarn of youth, ambition, and hope. In recent years, the trope has become a reality. The number of farmers in the United States alone has been steadily dropping. The percentage of first-generation farmers is close to 78%. It can be a tough business. Climate cycles are becoming unpredictable and, as in many industries, one just can't find enough workers. That's where integrated circuits come in. One farmer has the ability in today's world to augment his efforts through sensors, drones, and microcontrollers to compete and run a farm with what might have required a handful of humans in the past. In fact, only about 1 in 4 young farmers still use the traditional methods passed down over the generations. The reason? Automation and the rise of machine learning. How could microchip technology help the farm of the future through automation? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Returning to the podcast are Ross Satchell and Toby Sinkinson. Ross and Toby are applications engineers at Microchip Technology working out of the 8-bit microcontroller business unit. They join us today from our global headquarters in Chandler, Arizona. Welcome back, guys. Thanks for joining us again on Beyond the Microchip. In the intro, we briefly talked about automation in farming and the explosive growth of machine learning algorithms and integrated circuits to augment traditional methods. The last time we had you on, we touched briefly on the uses of automation and where farmers are augmenting that with microclimates and testing the soil and so forth. But let's do a really, really deep dive on it. So where do we start? Give us a brief sum of automation in farming.
You know, it's funny because I was thinking about this question the other day, and you know what came to mind was when I first learned object-oriented programming, my instructor actually brought to us not Java, but the story of Eli Whitney and the cotton gin. And the way that it's a great analogy. It's funny because you don't normally think of as farming as being, you know, the seed for technology, but really it was this whole idea of being able to replace, not having to replace an entire machine, but to have to replace just a portion, a module, in order to keep that thing running. Now, the cotton gin had a huge effect, and it's not the best moment in human history in terms of what it led to with slavery and that kind of things. But the same kinds of ideas with the way that that automation is still very present. It's present in our microcontrollers, the ability for these farmers to add sensors, remove sensors, and be able to accomplish an industrial process in a much easier way.
I mean, you're talking about specialization here, right? The cotton gin, if I recall correctly, was a machine that took seeds out of the cotton and it just greatly increased efficiency and moved things along?
Yeah, I think that seeding process is also very painful and very tough to do. But it sped up the whole thing. They were able to get these much larger yields, but mainly because of that factor. Like they didn't have to just replace a whole machine. It could be up and running very quickly because you just had to replace the part that worn out.
What else in terms of automation?
Okay, I'll add to that also in that I think we're seeing a similar kind of trend where it's the big industries that have that large yield, the big R&D budgets that are able to implement a lot of technology that it's more readily available. But here, the small farmer can be left behind. And so I think one of the joys of what we've done is provide a way that it gives an entry to some of this technology that is so powerful to people that, you know, it might be out of reach.
And so we're seeing, as you mentioned in the intro, like the children of farmers increasingly opting for other career paths. And so this means this tribal or generational knowledge has been lost. And so for younger people trying to become farmers, the access to land and also the ability to purchase it are turning out to be the limiting factors. So we accessed this National Young Farmer Coalition survey from 2022, and it was saying that almost 60% of young farmers said that finding affordable land was either very or extremely challenging, while 45% of young farmers said finding available land as very or extremely challenging. And a little over 40% was saying that just finding access to capital to grow their existing business was very or extremely challenging. And then for people who are Black, Indigenous, or people of color farmers, and that went up even more. Took it up to 54%. And then we're also seeing with the young farmers, they're naming that the cost of production being greater than the price that they actually receive for their products was very or extremely challenging, and that was 35%. So a little over a third of people, basically, it's not viable for them to remain continuing to farm. So this really is needs to push, or the push for automation, we're hoping will actually help these farmers to get back into the black and remain viable for generations to come so that they can continue to feed the country.
So one example of automation that I'm aware of was I saw a keynote speaker he was a tech guy. He was talking about telecom stuff, but he said, the future is drones. And he kind of went into a big, long lecture on drones, but he said, I'm a hop farmer. I'm from Wisconsin. So obviously he's a beer drinker if he's from Wisconsin. But the idea was he would send a drone out to go look for like brown mold and spider mites, on each individual hop. And he says, I don't want to do that by hand. He says, I'd be out there on my hands and knees and begging my kids and trying to scrape for workers. He says, but now I got a drone that can do that. I imagine that's just one of the multiple applications we're talking about here.
Well, a drone can be used as the ground truth for the rest of what you're measuring. So it used to be that the ground truth was going out and physically looking at what was going on. But if we're measuring things remotely with these sensors in the field, and then you use your drone to confirm that, for example, you could see that a particular part of your farm is performing poorly because it's not uptaking water, so that the moisture in the soil is remaining quite high, while other areas are drying out, meaning that the plants are actually taking up the moisture. Then you can send your drone out to that area and specifically and try and figure out why that particular area is not performing as well, and then identify what's actually going on and then treat just that area rather than having to, say, crop dust an entire crop when only, say, one small part of it is actually having problems.
Yeah, it's so easy to throw a camera on these drones and be able to just fly over and have that image detection and say, we fertilized this like 3 years in a row and it's still not doing what we needed it to do. So let's stop doing that there.
We also talked about moisture sensing in the previous episode.
Mm-hmm.
Can you break into that a little bit and talk about what the automation is of that? I mean, the farmer doesn't have to go out and physically grab the soil. What areas of automation can we get into regarding how we use sensors?
So there's a whole bunch of ways of measuring soil moisture. There's everything from really low quality and cheap resistive sensors to middle of the range capacitive sensors, and that sort of bleeds into frequency domain reflectometry, and then the really expensive time domain reflectometry, which are kind of the gold standard of moisture sensing. And we've actually found by playing around with the capacitive sensors, they tend to be skewed by the salinity in the soil, but we found several academic papers that were referring to by increasing the frequency that you operate these sensors, that slowly reduces the amount of skew that you get from the salinity in the soil. And then we did some experiments, and we found that ourselves, that our data actually reflected what we were reading about. So you can do fairly low-cost soil moisture sensing and still get pretty decent quality results.
You still have like this problem of calibration. And so the type of soil, so it's like its salinity and its temperature also, so that they fluctuate every day, the soil in the morning and night, and that affects the sensitivity of that reading. And then also that whether you have clay, loamy, or sandy soil, you have to, each of those sensors need to be calibrated to get an accurate measurement there. That goes a little bit back to the machine learning, because if you have some way of measuring those things, then you could adjust it on the fly there. But it's funny because I also saw recently, in a low cost design, they actually ended up just threw in a temperature sensor, and they're able to kind of gauge just with a simple temperature sensor what kind of moisture is there. So I think, and farmers, like we've talked before, like they play around with this crudeness game. Sometimes you can get away with something and make it very useful. And sometimes you actually do need the much more precise data in order to arrive at where you want. And so I think we're in that play of like, as this stuff is being developed, that you have to make those choices. It's engineering. You know?
There's the concept in design engineering of good enough. You don't necessarily need the best quality, high performance part to do a particular thing. You need something that is good enough to address the need that you have, and you don't need. It's kind of like driving a Ferrari to the corner store to buy a loaf of bread. Can you do it? Sure. Is it a good use of resources? Probably not.
And even today's crude is probably better than yesterday's perfect, right? In the last episode, you talked about taking a soil sample reading in situ versus sending it to a lab that may take a week or two. Well, the soil 2 weeks from now is not the soil today. So you might have missed out on 2 weeks of productivity yield, right?
Absolutely, because there's that it's not just that particular place on the farm, but it's also a single snapshot in time. So if you can not only get multiple areas on the farm, but multiple moments in time, then suddenly you have a very clear picture, or a much clearer picture, of what's actually going on in the farm.
You guys mentioned something last episode that kind of really, really piqued my curiosity, was the idea of microclimates. When you think of a farm, you think of, I'm oversimplifying here, but think of a cornfield in Iowa. As far as the eye can see, there's no mountains. There's maybe a couple of water towers, but it's probably not cloudy, or there's really no indication that there's really a lot going on climate-wise. Can you guys break down the idea of microclimates, how they show up, maybe how we measure them?
I think maybe the monoculture is not the best way to approach that, but I think like if you have different kinds of plants at different heights and different, so as moisture as the day starts and the sun comes up and the moisture is released and the humidity, here in Arizona we see like a crazy thing happen in the morning where that once the sun comes up the humidity just plummets. But you can have like, so maybe like if you're looking up, well, this is what Chandler, Arizona says on my phone it is, but if I look at my sensor that's just in my companion planner out here, I can see actually that it's more, the effects of having these leaves closer to the ground, trapping moisture there, means that what we're seeing there is different than what you're seeing, by a sensor out at the airport, so.
But that would allow you to tweak how you water it, when you water it.
You don't want to be watering your garden based on the airport. You want to be watering it on what you have right here. Yeah.
So we've got sensors. We talked a little bit about power sipping LoRa. Are there elements of automation that we can use with that technology?
So we're using, at the moment, it's taking a data point every 3 minutes. And then part of that is to do with the fair use policy for LoRa, that you're not spamming the channel all the time. And for the demo purposes, we're taking that reading every 3 minutes and then sending it immediately. But for an actual agricultural application, you'd probably use something like an EEPROM to store a day's worth or half a day's worth, something like that, worth of readings, and then send that all out at once. Because often just getting the radio connection is a significant part of that radio budget. So then sending the data comparatively, if you send it all in a big chunk, then it makes it far more efficient.
Going back to the example we brought up last time too, with the flood irrigation farmer who's watering his orchards at the end of the row, we have a situation where during that watering time, you want to be frequently sampling, like in that 3 minutes range. But the rest of the time, once that's done, you don't want to be wasting power sending that information, because largely for 6, 12, even 24 hours, that is going to remain pretty constant. It's just during those periods. So being able to dial in exactly when you use the radio is a really important part of the power saving process.
In comparison to the old ways versus the new ways, was my interpretation is that when the farmer went to sleep, that was when the farming stopped. And then the next morning when the farmer woke up, that was when the farming began again. But I would imagine with automated technology and integrated circuitry, there's stuff that's happening all day long. Is there the 24-hour cycle in digital farming, so to speak, or smart agriculture?
Absolutely. Because, for example, you have soil respiration. So during the evening, where often the soil will start to respirate carbon dioxide. And then later, in different times of the day, then start like reabsorb that CO2. So it's really enabling you to see more closely what's going on, and then what you can actually do about it, and what things you control, the things you can control, and manage the things that you can't control is probably the best way of putting it.
Yeah, it came to mind is maybe a little tangent, but that same farm that we were at, they have a hive there, and in the cold of the night when there's a potential for the colony collapse, being able to have some sort of alarm trigger to notice that this colony is getting too cold and be able to warm it up in the middle of the night. Yeah, you wouldn't know that as a traditional farmer, but being able to have access to that is the total difference between whether your apples or whatever your peaches are getting pollinated the way you need them to.
Yeah, because colony collapse is a big deal. So that's good. Help indicate that.
No, I think was it Einstein who said if we lose the bees, we have 2 to 3 years tops.
I've seen some scary images out there, and if we can find some for the episode, it's here's what your food looks like, and then minus the bees, and most of the pictures grayed out.
Mm-hmm.
So the idea of using technology to be able to at least monitor the bees before we talk about anything else, that's of huge value to farmers nowadays. So we've got radio, we've got sensors, we've also got kind of what you opened up with the cotton gin, Toby, is when we're talking about microcontrollers as a specific purpose, when we're talking about embedded control. Where are the areas that microcontrollers can add some real value?
Well, particularly our 8-bit devices, like they're very low cost. They're very easy to work with. All of the programming environment is very easy to jump on board with. And you can try different sensors. Adding sensors is a very easy thing. So it makes it a very flexible design. And it's amazingly powerful, like to be able to handle these radio, different kinds of radios, sending that information. They're a piece in that.
So one of the big places where 8-bit really shines, because cost is now pretty much on parity with 32-bit devices, but it's the low power aspect. And if you look at the data sheet minimum power consumption, then 8 and 32-bit devices look like they're comparable, but it's only when you actually dig a bit deeper you realize there's more at play here. Because with the 8-bit devices, we have a really quite a wide array of analog and digital peripherals. And what this enables you to do is put the device into one of the low power sleep modes, and only when a very specific set of variables happen, that's when you wake up and turn the CPU back on and process that data and do something with it. Versus often with the 32-bit devices, you tend to wake up on every interrupt and then determine whether or not you actually need to be awake. And that uses a significant amount of current. And then you go back to sleep again. But with the 8-bits, you just stay asleep until you actually need to do something, and then you do it. So that's really where 8-bits shine.
Yeah, and our peripherals are way more sophisticated than they've ever been. Like, on the device that we see here, like that where we were talking about driving this capacitive trace in order to figure out what the dialectic of the soil is so we can make an assumption about the moisture there. We're using this timer on here that's driven at a much higher frequency than you would ordinarily think, because we can phase lock loop it and all this stuff. It's pretty exciting. There's a lot of advanced kinds of things that you can do.
Because the main clock has a maximum frequency of about 24 megahertz, and we were driving that timer, We were operating the timer, which drives the capacitive trace at 30-something megahertz, 32, 36.
Yeah.
So faster than the main clock. And that was the thing that we were talking about in the last episode, where it offsets the salinity measurement, or the way that salinity skews the moisture measurement. So when I first started thinking about this project, because a friend asked me about it, and my initial response was, give me 2 years in a team, and I didn't have either of those things. And so I said, well, what if we do a capstone project? And so we did a capstone project, and Toby was actually one of the students on the capstone project, who then became an intern at Microchip and is now a full-time engineer with us.
What would this go for if somebody were looking to integrate it into their farming system?
So when I was first looking at this, I wanted to see what off-the-shelf solutions already existed. And the ones that I was finding were around about $160 per node. And I thought that was prohibitively expensive. Mm-hmm. And I thought if we can get that to less than half, hopefully down to a quarter, then I feel that then this is potentially viable. And we've managed to get, in terms of just our bill of materials, in runs of 10, so that's not a very efficient way of costing it, but we're hitting around about $40, which is right on that 1/4 mark that I was looking at.
And then this is self-contained. What's the power source for this?
So it's a 2 batteries. And so when we were initially looking at powering this thing, one of the obvious things that people think of is, well, why not put a rechargeable lithium battery on there? And it sounds like a great idea until you live in Phoenix, Arizona, where it is routinely 45 degrees Celsius, which is around 115 for about 5 months continuously. And your lithium rechargeable batteries just degrade in that so badly, and they suffer.
Yeah.
For a little reference of those of you who are not familiar with the Phoenix area, in the month of July in 2023, we went 30 days over 110 degrees Fahrenheit. So yeah, maybe not that potential solution. How did you get around that?
Well, we started looking at other battery chemistries, and one that was pointed out to us was lithium thionyl chloride. Now, this is a primary non-rechargeable battery, but it has really great energy densities due to the lithium, but it enables us to, where we're aiming at the moment, we're still playing with some of the low power aspects of it, but we're aiming to get 1.5 years out of one set of batteries. And then hopefully those batteries then can be recycled so that the lithium in the batteries then can be reclaimed and used again.
Yeah, potentially even longer too. There's a whole nother stage too where we're testing, like I said, at sending that data less often, even just once a day or something might be enough.
So you would batch these, right? And how far apart would you spread them?
It depends. If you're doing something like an orchard, you might want to do, say, 2 per tree, for example, for say, avocado or fruit trees or something like that, maybe 1 on each side, so you get a better idea of what's going on rather than just that single data point, or maybe even 4 all around it, depending on how big the tree is. It's probably not ideal for a crop like corn or something like that that's planted really closely, because you're going to see significant attenuation of the signal just due to the amount of material that's in between the device itself and the gateway that it communicates with.
Mm-hmm. So do they work in pairs? Do they talk to each other in pairs, or are they individual?
Each node is its individual data point, but it talks to, in this design, to a gateway that's centrally located, like potentially like on top of a barn. It wants to be in a very high location or the top of a home, so that way you want as much line of sight with each of these nodes as possible. In the orchard design, we'd probably want to have this up like on the tree or something and have a way to measure something underground that way, like run a longer wire.
Because you said you can measure soil moisture and you can also measure air moisture. So these would go in various different places depending on the altitude or depending on which crop they're growing?
Correct. And also depending if you're using flood irrigation or not.
That's right. We talked about flood irrigation.
Adds a whole new set of problems that you need to solve.
And going back to the power thing, when we were demoing this, we had a fellow actually who does rooftop gardening in New York City also come up to us and says, "Hey, we are using LoRa. We love your design. We'd really like you to put in we have these great solar chargers. So being able to harvest sun energy, solar energy would be fantastic to add to this as well to get around, especially here in Arizona, right?"
And so they're capturing the solar energy, but they're charging a supercapacitor. So rather than a battery, which has a limited number of either charge cycles or a limited lifetime in the example of a primary non-rechargeable battery. So we want to play around with that in the future and see if we can get that to work. Because if we can, we're potentially looking at probably 20 years out of a sensor node, because it's basically the lifetime of the silicon at that point probably becomes the bottleneck.
Yeah, it's not the capacitor. I think a little bit what we discovered too is that depending on how durable you want the coating on top of the solar, that's the piece, especially with the UV we have and how quickly that'll break down. I think there was a 5 to 7 year kind of thing there. But if you used glass or something like that, you could go much longer.
That's one of the things I noticed about embedded control technologies and some of the products in our mix is people think about Moore's Law, as in every 18 months I'm supposed to replace my laptop or my phone, whereas this is decades. We're talking about really having these out in the field, and we don't like to obsolete products. So when you design something, expect it to go the duration, right?
Yeah, it feels better to make something that's going to last, honestly, that's not a waste of resources. And
adding to e-waste and in the application where you don't need a huge amount of processing power, then why use the latest and greatest when good enough, which is something we talked about in the last episode, was the engineering concept of as long as it's good enough to meet the needs of that particular thing, then that's fine, rather than being the latest and greatest device that has all the bells and whistles.
That's the driving the Ferrari down to the corner store, right?
Correct.
You
Correct.
can do it,
to
but
get the
why
loaf of
would you?
bread. Yeah, why?
Okay, so let's suppose one of our listeners has a use case for this technology, or listening to us talk about it, maybe something novel popped up in their head. Where would we send them? Where could they go?
There's a great Hackster article that we wrote that walks through it was the Capstone project that Ross mentioned that I developed that later became this device here that we're holding. But that one is great because all of the things here were based on that prototype, and that all of those are available. All the parts, and the steps to walk through and recreate it yourself are right there. It's easy to follow. So I would point them there. We can add that.
We'll make sure we put that in the show notes.
Yeah, that's great. Thank you.
Okay, so we get to the question that I like to ask of all of our guests is we're talking about predictions on where the direction is going. So in this case, we're talking about agricultural automation. We talked about sensors, we talked about radios, we talked about LoRa. Where do you guys see automation going from here in terms of agriculture?
We need a lot more automation, because we've seen over the decades the number of people working on farms and generational farming getting less and less, or fewer and fewer. And so we need to see an increase in that. And we're also have some young people that are getting into farming. They're going to need as much data as they can, because if they don't have that tribal or generational knowledge that's been lost from people who've left the farms, then they need some way of figuring out what's going on without just doing trial and error and failing and losing their shirt in the process.
Yeah, the thing that just popped into my mind too is this. We saw a video of a design for this harvester, orchard harvester, where there's like these drones come in with these like cameras to evaluate whether the fruit is actually ripe or not, and they suction them, they pull it off, and then they weigh them, and that point is stamped. Like it's pretty amazing. I mean, we're gonna see some amazing things happening to our farms in the next few years.
Yeah, and you were talking something about that where there was like a net over the propellers so that it wouldn't affect the tree.
Yeah,
so the branches don't get stuck in and crash your drone.
Yeah. So you're effectively removing somebody from having to go out into the orchard and physically pick, but then somebody has to design the system, somebody has to maintain the drone, and somebody has to make sure that the drone is ready to go when needed. It's probably got a dock, it's got to recharge. So there's lots of opportunities for expansion of other skill sets on the farm, right? Not just going out and eyeballing the produce themselves.
Absolutely. There's the common misconception of any new technology that makes people unemployed, but that's only a small part of the picture, because a larger part of the picture is that, sure, there are certain job types that become redundant, but a whole new type of employment often arises, and in directions often we can't even predict. And so it's both an exciting and terrifying time to be alive.
Yeah, the analogy that I like to think of in terms of automation, we usually have this kind of discussion in, what is large language models going to do to the creative process? But if you think about a conveyor belt system, like an assembly line, right? You've got certain inputs. At some point, a human comes and adds something to that product. The easiest one to think of is probably cars, right? As the frame moves its way down the assembly line, somebody bolts on a certain spot. When you add part of automation to that, your yield dramatically increases. So on one side, you create a vacuum that's just sucking demand in because the automation is moving so fast. And on the other side, the supply goes through the roof because that yield is so high. So on one side, you need more people or more processes feeding inputs. And on the other side, you have to have somebody to process the outputs. And so I don't like to think of automation in that sense of something is going to replace a job. It usually creates many more jobs, if not for the non-automated part, than for the result of what happens when you put automation in. So in this case, let's do our orchard example. If you've got a drone that's picking more fruit, somebody's got to do something with all that extra fruit, right?
Yeah, I think, and that I think we mentioned earlier, was it this episode or the last time, but just the changing, the climate cycles, right? Like being able to respond more effectively and efficiently to those things is absolutely going to require that automation, or respond to pests or disease in a way that you can be there when it's something, if it's a disease infestation when it shows up, when you can respond to it right away, it's a big difference.
It is often the likelihood that you can get something still viable from that crop is greatly increased at that point, rather than it progressing to the point where now the entire crop just is a lost cause.
You guys are talking about reduction of waste.
Absolutely.
That's good. We'll have to have you guys back to talk about that, because that's definitely a topic we need to discuss. Ross Satchel and Toby Sinkinson are applications engineers at Microchip Technology, working out of the 8-bit microcontroller business unit. They join us again today from our global headquarters in Chandler, Arizona. Thanks for coming in, guys.
Thanks for having us.
Thank you.
Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.